thing. I pull back some closed form from here, and I evaluate it on some cycle, actually on the fundamental cycle in S1 cross S1. So I can also write it in the following way. So this is this integral is a pullback of the homology class of omega, evaluated on a fundamental class of the torus. So this is a quantity which is now given completely in topological terms, right? So this kind of geometry or field theory kind of disappeared, and I obtained just this very nice expression, right? As we discussed last time, that's probably one of the definitions of the linking number. It is obvious that if I move gamma 1 and gamma 2 inside R3, if I move these maps without allowing intersections, then this expression will not change, right? By homology invariance of the pairings between homology and homology, right? So here there is nothing that changes unless I touch the diagonal, right? Of course, if I touch the diagonal, then the expression may change. So this is a manifest topological invariant. So here it's also obvious that if I choose different representatives for omega, the result does not change. So I can choose this very nice representative, the standard rotation invariant form, or I can choose the singular representative that we were using before, right? So this Dirac mass at the north pole, the result must be the same. And for the Dirac mass, I invite you to check that actually this will be exactly the expression we had last time. So, so that was a kind of reminder and extension of the abelian story. Now let's pass to the non-abelian story. So should we do the variant then? So that's probably the natural.
Okay. All right. So let's try to do the non-abelian. The non-abelian story, and let's see, at least in some sketchy way, what kind of, so some of the things we can still make work in the non-abelian setup, some of the things possibly not. And now we should really make contact with other courses, right? Probably with quantum topology, and also with Poisson geometry and quantization. So we'll see some links. So let me, perhaps before we proceed, let me make one more remark here that I forgot. So recall we said S of A is 1/2 integral A dA. But in principle, we can introduce here some coefficient, let's say lambda. So if we introduce such a coefficient, then what will happen? So this basically means that our operator G is multiplied by lambda. So its inverse should be scaled by lambda inverse, right? So this G, whatever it is, it will receive some lambda inverse coefficient. And here it will also be lambda inverse. So there is such a scaling, and we're going to use it in a second. So the non-abelian Chern-Simons. Now A will be one form with values in the Lie algebra. And let's choose for today G to be SU2. So this means 2 by 2 complex matrices, trace x equals 0 and x star is equal to minus x. Now, I don't quite remember how we were writing it. So Chern-Simons of A. Did we use the notation with a trace, or did we use the notation with the pairing on the Lie algebra? Yeah, I think trace is probably easier. So trace, and here there is some funny expression of this form, right? And one possible rewriting of this one is 1/3 A bracket of A with A, right? So that's the expression. So there are many aspects of this problem that we should discuss. First of all, let's look at the quadratic part of the action. Right, so the quadratic part of the action it resembles very much what we were doing before. Right, so this is 1/2 trace integral of A dA. Now, well, let me do the following. Let me introduce EA an orthonormal basis in this Lie algebra with respect to this trace. In fact, here I'm cheating a little bit. Trace is negatively definite on this set of anti-Hermitian matrices, so I should say orthonormal with respect to minus trace. But let me forget, like, anyways, like all the signs and coefficients, I will be very shaky about them. So, but here, notice that there is a little bit of cheating. So then I can say that my one form is a sum of coefficients times the basis in the Lie algebra times the basis in the set of one forms, right? So that's the expression for A. And in particular, I can also write it as sum over A, EA. So these are now one forms, right? So these are scalar one forms as I had before. So how does this expression look like then? Well, it looks like 1/2 sum over A, and here integral AA dA. So in other words, this is just the sum of 3 copies of abelian Chern-Simons theories that we had before, right? So that's how it looks like. Maybe I can also write it down in the following funny way. So you see, I now have a summation over 2 indices, and I have the Kronecker delta to make A is equal to B. So this is just to say that my operator A, the quadratic form that I would like to invert, is now the identity map, the Kronecker delta, times the de Rham differential. Well, what about its inverse? Well, since we already know what to do with D, we already have experience here, this means that for A minus 1, we can simply keep the identity map, right, this delta AB, and multiply by whatever G we want. Let me denote it G omega, right? Recall, we now have a family of G's which depend on the volume form on the sphere, right? So this would be a valid choice. So omega is a generator of the top degree cohomology of the two spheres. Right? So that's basically here all our experience of the abelian Chern-Simons applies. Now let me briefly discuss this term. So the so-called interaction term. So how does it actually look like? So let me write it down for you in terms of those components A, I, A. Right? First of all, so there are three A's. Let me call them AIA, AJB, and AKC. Now, well, this is a three form, right? So this means that, so these indices, I, J, and K, they should enter with a signature of the permutation, right? They should all be different, and they should be signed corresponding to the signature of the permutation. And we already know how to do it, right? They should be paired with this epsilon ijk tensor, and we should have a sum of ij and k. Now, what about these indices? So what does it actually mean when we make a substitution? This means that here we put a trace of EA, EB, bracket EC. And the sum over A, B, and C. Okay. So in any event, let's remember that there is such an expression, but let's also say what it is. So do you think what is going to be? Right? So A, B, and C, they also take values 1, 2, and 3, right? The SU2 is a three-dimensional Lie algebra. So how do these things going to look like? Yeah, it turns out just by chance for today, epsilon finds maybe up to a coefficient. So it will also be epsilon ABC. Maybe that's a good exercise. Check it. That for SU2, indeed this is the case. It's obvious that it should be invariant under the anti-invariant. So they should change sign when you exchange B and C. But why? For instance, do you think why is it symmetric under cyclic rotations?
Well, we already know that the expression is.
I think it's easier. If I'm not mistaken, it's easier than that. Like if you just write it down as EA, EB, EC minus EA, EC, EB. And then cyclically, right, this is under the trace. So we can cyclically rotate because trace is cyclically invariant. So if we do this rotation, then in each of the terms, then we'll see that the indices here also move. So it's because of the, I think, cyclic invariance of the trace. And, well, there might be some coefficient. Right. So that's how it looks like. Now, how do we draw it? So there is a Feynman calculus. So this is a cubic term in our action. And this means that there should be a triple vertex. Right? So corresponding to this gadget, there is a triple vertex. So this triple vertex here will be labeled by indices IA, JB, KC. And the vertex itself, right, it should be a tensor, it should be a function of those indices. And this expression tells us what it is. Remember, there were some kind of multilinear forms sitting at the vertices in our Feynman calculus. So what is it that's sitting here? It's epsilon ijk, epsilon abc. Right? So that's the expression sitting here. Right. Now, so this implies that we have the following Feynman rules. So when we study the expansion of the three-dimensional Chern-Simons theory, we have graphs with trivalent vertices, and a priori all the loose ends should be tied, right? So that's an example of a graph in the Feynman expansion of the Chern-Simons theory. You're only allowed to use trivalent vertices. However, if we want to introduce some linear forms in the game, right? So then we are also allowed to have univalent vertices where our lines would end. So this is in case we have extra linear forms. Now let me state the goal for today. And I'll formulate an ambitious goal, and then I will downgrade it at the next hour. So we would like to take a simple closed curve, a map from S1 to R3 without self-intersections. In other words, this is a knot in R3. And we would like to define the expectation value W gamma of A. So let me recall that W gamma is the following expression. So this is a trace of 1 plus integral along gamma of A plus an iterated integral A of T1, T2 along gamma plus higher iterated integrals. So, right? So that's the Wilson loop expression in non-abelian gauge theory. So we would like to define such an expectation value in the Chern-Simons theory. So this is it's expected to be not invariant. So this is essentially because the expression for the action is diffeomorphism invariant, and expression for this trace of holonomy is diffeomorphism invariant. So if quantum theory has the same features as a classical theory, this should be a diffeomorphism invariant expression. And what is it in nature, right? So this is expected to be a formal power series in our quantum parameter h, right? So we expect to have some series, some formal power series in h, and its coefficients should be numerical, not invariants, right? So that's a dream of quantum topology. Now, at the next hour, we'll try to see kind of at least what part of this dream comes true or doesn't come true. Okay, let's have a break. All right, let's continue.
I was referring to the material because the content is also the last.
All right, so there are several issues that we should discuss. So we're computing the expectation value of this expression. So this is a sum of integrals of polynomials of A, right? So this means that we're allowed to have an arbitrary number of loose univalent ends in our Feynman graphs, because we can have an arbitrary number of A's in those integrals in W gamma of A. So that's the first thing. Now, well, let's first look at the H degree count. So recall that different Feynman graphs will contribute some numbers, will contribute something into the result, and there will be H to some power, right? So H usually enters in the power the number of edges of gamma minus the number of vertices of gamma. However, this recipe we worked out in the case when there were no linear forms or where there were no polynomials in our expression. In fact, so as you see here, those A's, they don't carry any degree of H. So therefore, you shouldn't count those univalent vertices in this degree count. So, which means plus the number of univalent vertices. So only trivalent vertices are counted here. So let's look at the simplest Feynman graphs that we can have. So what about the degree of H equal to 1? Let me give you the answers, and then you will tell me whether you agree or not. So I think for this we only have one possibility. Maybe let me first state one more thing. So let me recall that the number of edges minus the number of vertices, we can also compute it using the Euler characteristic of our graph. And so this will be the sum over L, let's say, connected components of gamma. So here we have the number of maybe let me say S. So the number of loops minus 1, right? So that's the expression. And then plus the number of univalent vertices. So this is a more practical formula for computation of this number. So if the degree is equal to 1, I believe there is only one possibility. So that's a trivalent graph without any trivalent vertices, right? So the number of trivalent vertices is actually equal to 0, right? So there is only one connected component with 0 loops. So the first expression gives you minus 1, and the number of univalent vertices is 2. And I don't think there are any other options for creating. Trivalent vertex, yeah, let's look at it. Right, here I think, right. Yeah, this, let me see, this also works. Right. So, so here will be 0 plus 1 is equal to 1. Okay, yeah, let's talk about it as well. That's right. So now for degree equal to 2, right. But now you correct me. Maybe what I say is wrong. First of all, there is such a disconnected graph. So minus 2 plus 4 is equal to 2. So there is this trivalent graph with minus 1 plus 3 is equal to 2. Then there is this guy. So here 0 plus 2 is equal to 2. But then how is it? Would we also have something even more singular? Can we have something with 1?
I'm sorry, but like in the first situation,
Yeah.
the graph with two loops, two vertices, two loops, and just like the same and the edge, it also should work.
So which one?
So like the same as the second one, but just with one more loop on the other vertex.
Again, what?
Like the second loop on the other vertex.
Oh, the second loop on the, okay, yeah. Let's see. So no external vertices at all, right? So minus 2, 0 plus 0. No, what I'm saying. Yes, 2 minus 1 plus 0 is equal to 1. Yeah, sure. Okay. Very good. Here would we have, probably we would have more exotic stuff. Would we? Maybe like two graphs like that. More stuff.
Isn't it the case that we can take any two copies of the three first graph? Because
Yeah. Right, so this similar to this one, right?
And we could also mix them. So take one copy of the one graph and another one of the other. So they're quite a lot.
Say again?
Just take
Yeah, right. Okay, so this any combination of those. Okay. Right. So not all of them will play. Not all of them will play a role in our further considerations, but these are maybe not a complete list. So these are some of the low degree contributions. Right. So now let's discuss the Lie algebra combinatorics. So what are the contributions? Let's see what are the contributions of those graphs. First of all, there are some integrals, but that we consider a bit later. Let's look at the factors that we get in terms of Lie combinatorics. Right, so for instance, this guy will have Lie algebra indices A and B. There will be also the indices I and J, but for A and B, it will be the identity map, the Kronecker delta, which corresponds to it. Right? So what about this guy, for instance, right? So you have here something which is called A. Here we have B and C, and sitting on this edge, we have the identity map delta BC. Sitting at the vertex, we have epsilon ABC. So the Lie algebraic factor that we get here is sum over B and C epsilon ABC delta BC. Right? Actually, this is nice because this is skew-symmetric, this is symmetric. So this factor is simply equal to 0. So yes, there is such a graph in the expansion, and its coefficient is equal to 0. So this guy is gone. So this guy similarly, right, is gone as well. And as a consequence, all this garbage is also gone. Right? In fact, it's not there. Now let's look at these two graphs. So where would they come from? Recall that they're coming, so those loose ends, they're provided by the Wilson line, right? So this means that there was already a trace of the corresponding, so there is here. In fact, this situation may occur in two cases, right? So we have our integrate, so this is our curve. So we're inserting 4 copies of A, right? Because we need 4 loose ends for such a graph to fly. And then they can be connected this way or with a cross. What happens if they are connected in this way? Right? We have EA, EB, EC, ED. So these are the generators of our Lie algebra along the curve. And we're inserting here delta AB, delta CD. Okay? So how does it look like, the corresponding contribution? Well, so that's a trace, sum over A, EA squared, sum over C, EC squared. Sorry. You probably know of such elements from the elementary theory of Lie algebras, right? So quadratic expressions in terms of generators. Do you know one famous quadratic expression? The quadratic Casimir element. So does it ring the bell? Not quite? Okay, so for the case of SU2, let me choose EA is equal to 1 over E, let's say E1, 1 over square root of 2, 0, 1, minus 1, 0. E2, 1 over square root of 2, 0, I, 0. And E3, 1 over square root of 2, I, minus I, 0. So then check E1 square plus E2 square plus E3 square is some coefficient times the unit matrix, right? So the thing is that this guy commutes with everything, right? Therefore, this trace is equal to 2 times C squared, right? C is this value, is a coefficient in front of the unit matrix. So these are actually unit matrices with some coefficient. Okay. So another remark. What happens with this expression? So this expression corresponds to a trace, EA, EB. And we said that we have delta AB there. So the corresponding factor is 2 times C.
degree one, there's also two trivalent vertices, all the edges are connected to each other.
Yeah.
I don't see it.
Yeah, right. So let me make two more computations. So actually, this diagram may also look like that. Right? So this corresponds to the, again, trace, EA, EB, EC, ED. But here we have delta EC, delta BD. Well, that's a different type of expression. Let me do the following. So this is sum of AB, trace, EA, EB, EA, EB. Let me commute EA and EB. So this is equal to sum over A and B, trace, EA, EB, EA, EB, plus trace, EA, EB square, EA. Notice that by cyclicity of trace, this is our friend from before, right? So that's the same guy as we had there. So this is 2c squared. Now this is a new expression. We can also compute it, but let me rewrite it in the following form. This is sum over A, B, C. C, I hope there is no confusion when C is an index and C is a value of the Casimir. And here epsilon ABC trace EC, EA, EB. So I just put the bracket of EA and EB, epsilon ABC times EC, and I obtain this expression. So we see that this diagram gives two contributions. So one contribution similar to what we had before, and one contribution is kind of different. Maybe the last question, what happens with this gadget? So this gadget corresponds to trace, EA, EB, EC, and now there is a trivalent vertex. So recall that the value of the trivalent vertex is epsilon ABC, right? So this guy gives you the same coefficient or the same expression as the guy we got there. So this one splits into one contribution which looks like that, and one contribution which looks like that. Okay, so that was about the numerical factors which come from Lie theorem. So now we have a control over H, and we have some control over numerical factors coming from Lie theorem. Now finally, what about integrals? Let's see what happens with integrals here for this contribution. So this will be an integral of T1 greater or equal to T2 greater or equal to 0. And here we are supposed to compute A of T1, A of T2. So let me write down this integral explicitly, and other integrals I'll try not to write explicitly. So what does it mean? This means the following. Let me say, so we have those parameters T1 and T2 on my curve. Right, so here I'll have dxi over dt t1 dyj over dt t2, and here I'll have g ij of gamma t1 gamma t2 sum over I and j dt1 dt2, right? So that's so A is a one form, right? So here I'm writing explicitly the integrals of one form of a, so here I'm using this formula. So integral of gamma is the integral dxi over dt ai gamma t dt here from 0 to 1, right? So that's just a definition of an integral of a one form along a curve. And now I'm substituting the Green's function for the correlate of AI. And here there will be also, right, AB times this trace EA EB, right? So that's the least erratic factor. Right. So the coefficients should be given by those integrals. The problem is that this integral typically does not make sense. So this is in no sense a convergent integral. Therefore, it's not going to give us any number. It's a little bit expected, but I told you in the beginning of the course, we're not going to do any divergences in the course. But unfortunately, you see, it's not quite possible. We need to do something about it. So let me make the following suggestion. This is not a real recipe, but it will do for the remaining 15 minutes. So we're computing this expression for the Chern-Simons for G equal to SU2. And already we see that the first coefficient does not make sense. It is a little bit to be expected. Remember that already last time I was saying that such an expectation value in the abelian Chern-Simons theorem does not quite make sense. Right? So let's try to make sense of a difference between this expectation value and the abelian Chern-Simons. Recall that in the abelian Chern-Simons, I could introduce some parameter lambda, right? Just by scaling the action. So let me scale the action in such a way that these contributions, the meaningless contributions would cancel. After all, recall, this is just the same integral because this is Gij abelian times delta AB. So the only thing we need is to gauge the numerical factors such that they would cancel. What's the numerical factor here? So the numerical factor here is equal to delta AB trace EA EB. So this numerical factor is equal to 2C. Right? Yes, this numerical factor is equal to 2C. And remember that here in the abelian Chern-Simons theory, we would be able to put the parameter lambda minus 1. So we can always choose lambda minus 1 equal to 2C such that those divergent contributions cancel. Right? So here we have a contribution that I've written here. In the abelian Chern-Simons theory, I have a similar contribution without Lie algebraic factors, but with a coefficient lambda minus 1. Simply choose them to cancel. Right? So, so then in degree 1, we hopefully get a cancellation. Now, what about the degree 2? So let's discuss this. So I take non-abelian minus abelian. I have this guy, I have that guy in the non-abelian side. I have this guy. I have this guy. Possibly I have some other stuff, but let me ignore it for a moment. What do I have on the abelian side? Well, of course, I have this guy. I have that guy. And do I have those diagrams? Not really, because in the abelian case, there are no trivalent vertices, right? So that's it. That's what I have on the abelian side, right? So I know that this guy gives me something like 2c squared. So this guy gives me some 2c squared plus this epsilon ABC trace EA, EB, EC. So this guy gives me epsilon ABC trace EA, EB, EC. And this guy we even don't know, right? We didn't compute it. So let me choose a coefficient here. Again, so this integral is really very bad. So this integral is more or less a kind of copy. The singularity of this integral has more or less the same nature as the singularity here. So when these 2 points are approaching each other, we get something very singular, and it does not make any sense. So these things we should really cancel if we have any hope to obtain a meaningful result. So let me choose the coefficient here to be 2c squared, the coefficient here to be 2c squared. So then, so these guys disappear. This cancels that. What remains is this guy plus that guy plus this guy. Now I have to tell you that I was cheating a little bit, and I forgot a part of the story. Recall that in the finite dimensional setup, we were talking about gauge fixing and Faddeev-Popov determinants, right? So in fact, in this story, there is a Faddeev-Popov determinant, and it cancels, and it eats this guy. So this is also some bad integral, but it is cancelled. By Faddeev-Popov determinant. So this would probably require too much of technology to introduce it. We would need some kind of fermionic integrals and so on, a little bit in the style of the exercise that we once had on the Grassmann algebra. So there would be a contribution with an opposite sign with so-called Faddeev-Popov ghosts, which would cancel this diagram. Now what remains is the sum of these two diagrams. Now let me state a theorem and discuss it a little bit. So this theorem is due to Barnatan in the early days of quantum topology. And the statement is as follows. So the sum of these two diagrams, meaning the sum of the corresponding contributions in the perturbative Chern-Simons theory, has the following properties. So the corresponding integrals converge. This is, at least in a Barnatan, this is non-trivial and somewhat painful calculation, right? So this, the corresponding integrals, we'll discuss them in a little bit more detail in a minute. Well, in principle, they may have singularities. And it is some work to show that, well, singularities would typically enter when some of the points collide, right? So there would be here a situation when, for instance, this point approaches that point. Here there would be a situation when, for instance, this point approaches that point, and so on. So there would be dangerous situations, and one needs to prove that those integrals converge. So Barnatan is doing it for this round sphere choice of the quasi-inverse of the theorem differential. And, well, each of those integrals requires some pages of calculations. So that's the first statement. So the second statement. So the result is actually a knot invariant. So remember that for every knot, for every nice map from S1 to R3, we can now compute a number. So the number would correspond to the sum of these two contributions. In fact, the least theoretic factor you can throw out because it's the same, right? So this is this least theoretic factor times the sum of two integrals with some coefficient. And so the result is actually independent of diffeomorphisms. You see, it is a little bit of a miracle as we are talking about it, because yes, naively, the result was supposed to be a knot invariant right from the start, but then some of the contributions don't make sense because of the divergent integrals, and we had to invent some kind of cancellation procedure to get rid of them. So it's not entirely obvious why would this expression have nice properties, but it turns out it does have nice properties. So this is called the Carson knot invariant. I'm not sure, in your quantum topology course, have you looked maybe at Carson invariant of three manifolds, or not really? So this was not mentioned at all. So this is like, and here this is the Vasiliev invariants, were they mentioned in the quantum topology course? Wow. Okay. So but this is one of the simplest invariants you can invent. Now let's talk a little bit about the integrals and how kind of the idea of the proof. What did Barnatan do to show that this works? What happens here? What is the integral that we have there? Well, we have 4 points. We have 4 points on a circle, right? And we have an integral over the 4 simplics. Right? So this fourth simplex is first mapped into R4, right? Sorry, R3 to the power 4. So this is each of these points. So gamma T1, gamma T2, gamma T3, gamma T4. And then this cross, this corresponds to the fact that this R4 is mapped to the product of two spheres, right? So we take gamma 1, gamma of T1 minus gamma of T3 over the absolute value gamma of T1, gamma of T3, and gamma of T2 minus gamma of T4. So we take a pair of unit vectors. Now we consider a product of our favorite two forms, product of our volume forms. Maybe I should write it here. So let me denote this map, the combined map again by, so this map is N, this map is gamma 4. So my contribution is an integral over delta 4 over this simplex of N composed with gamma 4 star of omega 1 wedge omega 2. So these are two copies of the volume form, right? On the first sphere and on the second sphere. So that's what this integral is, right? Now, of course, there is a question whether it's a convergent integral, but okay, assume it's convergent, then, well, that's what we have. Now, what about this gadget? So this gadget is delta 3. So that's a 3 simplex, which corresponds to these 3 points on the circle, times R3. So this is an internal vertex. So the corresponding integration is over the whole of R3. Of course, eventually, we need to take out diagonals. And this is mapped to R3 cubed times R3 by gamma 3 times 1, right? So these points are there mapped to the corresponding gammas. And now this is mapped to S2 times S2 times S2, right? So each of these legs, it corresponds to a map to a unit sphere. So I take the unit vector, this point minus that point, this point minus that point, and this point minus that point, right? So let's call this map M. So the second integral is an integral over delta 3 times R3, possibly without some diagonals. And here it is M composed with gamma 3 star of omega 1 wedge omega 2 wedge omega 3. So these are two integrals expressed in a somewhat nicer geometric way. Now the problem is, even forget about possible divergences, assume that they are not there. So these spaces here, these are spaces with boundary and corners, right? So before, remember when we were defining the Lincoln number, we had a similar formula. And this similar formula, the space which would appear in the integration, this would be a nice compact manifold. Now, these guys are not nice compact manifolds. A priori, if we move our knot, each of these contributions is going to change because the boundary, right? So there is some boundary of the simplex. This boundary moves, at least its image in R3 to the power 4, it moves, and the value of the integral changes. However, the claim here that if we add them up with an appropriate coefficient, I forgot, maybe minus 1/2 or plus 1/2, whatever. So there is a coefficient here. So the change in one of the integrals will exactly compensate the change of the other. So that's the technical statement. And this is an interesting and surprising statement. In the proof that Barnatan gives, he actually finds a way to glue these spaces together to obtain a nice compact manifold where it would be more obvious that the result does not change. So this requires some imagination, because this guy is of dimension 6, this guy is of dimension 4. Before you glue them together, you need to do something. He multiplies by a copy of one more copy of a sphere here, and then after that he glues them together into some relatively complicated gadget. And in this gadget, the argument is similar to the argument for the Lincoln number. So, so equal to the some kind of degree of a map from the gadget that you glue from them to S2 times S2 times S2, possibly with some coefficient, something like 1/6, because you need to glue together many copies. So you see, this leads to interesting topology. It gives us something to think about, and people since Barnatan, they were thinking about it quite a lot. I don't think I would be able to present recent developments because I don't know them so much, and also because we still have only 3 minutes left. But let me finish with the following. With the following observation. So what's the problem? What's the problem with these integrals? As I said, the problem is that the corresponding spaces over which we integrate, they have boundary, right? And then usually an integral over a space with boundary doesn't seem to be homotopy invariant, even if you integrate a closed form. Right? So how do these boundaries look like? Well, you can actually guess it in some way by looking at the graphs. So for instance, this graph, so where would the danger come from? So the danger would come from like 2 points approaching each other, right? So it would have many components of the boundary. Let me draw one of them, right? So that's one, so a graph which would correspond to one of the boundary components. So these 2 points, they get close to each other. What about this graph? Well, also there will be lots of boundary components. But one of them is what? This point gets close to that point. So this may give you a similar boundary component. Now, the whole idea is that these boundary components somehow would cancel each other, right? Because we do want a homotopy invariant. Well, but then we need to know, like, kind of what boundary components would cancel what boundary components and with which coefficients. So this leads to the idea of a graph complex. Right? We have a boundary operator on our spaces, assigning to a space the corresponding boundary. One can invent an analog of this operator in terms of graphs. And so in terms of this graph complex, so we would say that this is a boundary operator in the graph complex. The statement would be like that. So the sum of these two graphs is a cocycle in the graph complex. roughly speaking, if it's a cocycle in the graph complex, the boundary contributions exactly cancel each other. And therefore, the resulting expression is a homotopy invariant. In this case, not invariant. And this is a general statement. I've shown you how it works, let's say, pretended to show how it works for this degree 2 invariant, but in general, how it works for arbitrary degrees. You define a graph complex, and cocycles in the graph complex define for you not invariants of higher degrees. Maybe the last thing to say, so this is, well, one can say nice, but a relatively painful procedure. I think what you see in Poisson geometry and quantization course, I don't know whether you discussed not invariants at all there in terms of associators. In fact, associators, Greenfield associators, that's another and in some way easier tool to think about the quantization of Chern-Simons theory and to think about not invariants. So that's an alternative tool which gives you the same results. So I've shown you how it works if you start with the perturbations theory. And so there is another approach which is called Kontsevich integral. This is more like quantum mechanics of Chern-Simons. And there is an algebraic, the third algebraic approach in terms of Greenfield associators that you see a lot, I understand, in a quantization course. And this gives you another approach basically to the same type of results. You can actually ask Pavel to tell you more about it in the quantization course. Well, we're a little bit over time, and well, that was the last lecture of this quantum field theory for mathematicians course. Thanks a lot for participating, and sorry that in the end, well, it got a little bit like fantasist rather than precise math, but I think probably it's better this way to end in a kind of at least some interesting results and interesting statements. Okay, well, thanks a lot.